thank the organizers for this opportunity to present my work in this meeting. So I will speak on universal corrections to entanglement entropy of local quantum quenches. This talk is based on this paper with Justin David and Prem Kumar. Consider a CFT with an excited state at the origin at 0 time. As the time progresses, we expect that the excited state will propagate along the light cone. When this excited state encounters the entanglement interval, L1 to L2, we expect that there will be a change in the entanglement entropy of this interval due to the presence of the excited state. This change is actually a step function jump, where the step function is 0 outside this entanglement interval L1 to L2, and there is a finite value of the change of entanglement entropy within the entanglement interval L1 to L2. The magnitude of the jump here is related to the quantum dimension of the excited state. So this is the plot, the red curve, which gives the jump. From these 2 points are the ends of the entanglement interval. Now this step function, the entanglement entropy has this step function jump when the width of the excited state is 0. So here there is an excited state. When the width is 0, then this is the entanglement entropy given by the red curve. This interval L1 to L2, so entanglement length, yes, it's this interval, L2 minus L1. So when this excited state has a finite width, when epsilon is non-zero, it is expected that there will be a smooth plot. So this step function will be smoothed out, and it is given by this blue curve. The shape of the smoothing will depend on the details of the CFT. However, we will show that the time dependence of the correction to Renyi entropy and entanglement entropy at order epsilon square is universal. These are the ends of the entanglement interval. So this L1 to L2. So what is meant by, how will we proceed with the calculation with this excited state? So for that, I will define an excited state density matrix. This density matrix is obtained by first considering such a time-evolved excited state. This state is obtained by acting on a thermal state with the excited state operator and then evolving in time. And the density matrix is obtained by taking the outer product of such time-evolved states. Here, rho beta is the thermal density matrix, and n is the normalization such that the excited state density matrix has trace 1. Now, a regularization parameter is used, epsilon. This is also the width of the excited state. So here, it is used in such a manner. What this means is that now instead of the operator O being on the origin, it is displaced in imaginary time by a small value epsilon. So now these operators are, instead of being here at origin, they are displaced in imaginary time. Now this density matrix is written in terms of holomorphic and anti-holomorphic coordinates, and this transformation is used to go from the space-time coordinates to the holomorphic and anti-holomorphic coordinates. Given this diagram, this is the locations of the operators on the holomorphic plane. This x1 is the location of the operator O, and x4 is the location of operator O dagger. And x2 and x3 are the locations of the endpoints of the interval. I stated that the excited state propagates along the light cone. So to illustrate this, it is seen by evaluating the energy density in this excited state. The energy density is calculated by taking trace of the density matrix times the TT component of the stress tensor. This amounts to evaluating this 3-point function of the TT component of the stress tensor along with the excited state. And this is the answer for the energy density. As you can see, as time at 0 time, the energy density is concentrated at x equals 0, at space coordinate equals 0. But as time progresses, this energy density splits, so it propagates along the negative and the positive directions. So this is the propagation of this energy density along the light cone. So thus, we say that the excited state propagates along the light cone. And the width here of this energy density is related to the width of the excited state epsilon. Going back to the density matrix, so here I show that the trace of the density matrix is given by a 2-point function in the thermal state. So this is seen by considering, by taking the density matrix and like acting on it with this I and I states, the same states, and summing over I. Now, these are just some numbers, so we can move around these correlators. And here, writing this I outer product sum over I as unity, we obtain this, this 2-point function is obtained. What this means on a complex plane is that the operators O and O dagger are evolved in time and brought to these locations in the upper and lower half plane, and then the upper and lower half plane is sewn together along the 0 axis. Similarly, the reduced density matrix for the excited state is obtained by sewing this upper and lower half plane together, but this region A is left out. So this, yes? Here it's here. Yeah, one when it becomes. This is how the trace is done to obtain the reduced density matrix of the excited state. Similarly, now we want to obtain the trace of n powers of the reduced density matrix. This is given by this 2n point function evaluated in a thermal state. And this 2n point function is evaluated on such an n-sheeted surface, where this is the original plane with the O and O dagger operators present. And these are the replica planes. Each plane has the O dagger operators and the entanglement interval. And so here is a more detailed diagram. So here, the upper and lower half plane is sewn together in each of these planes, excluding this region A. And along with that sewing, even all the planes are sewn together with each other. So the trace of n powers of the density matrix is obtained on such an n-sheeted Riemann surface. So what we want to do is evaluate the nth Renyi entropy. To evaluate the nth Renyi entropy, we require this trace of n powers of the reduced density matrix. Yes, so we need to go to this n-sheeted Riemann surface to evaluate. So as this trace was a 2-point function, now the n powers of the density matrix trace is a 2n point function evaluated on this n-sheeted Riemann surface. Evaluating the 2n point function on the n-sheeted Riemann surface is difficult, so what we do is we want to go to a plane. So this uniformization map is used to go from this n-sheeted Riemann surface to a uniformized plane, where the original sheet is mapped to the slice here. W1 and W4 are the locations of the operators now in this uniformized plane. And the entanglement interval, it maps to the 0 to infinity line on this slice. And similarly, each sheet is mapped to the other slices on the uniformized plane. Hence, the problem of evaluating the two-endpoint function on this complicated Riemann surface, it reduces to a problem of evaluating the two-endpoint function on a uniformized plane where the two-end operators are located at these points, W's. Also, the W points on each slice here are obtained by a rotation from the W points at in the original slice. And hence, we will now look at, the problem is to evaluate this nth Renyi entropy, and this will be given by essentially this two-endpoint function on such a uniformized plane. I will define these cross ratios, which are n powers of the ratio of the locations of the operators on the uniformized plane. As you see, this the coefficient of the I epsilon term, this sign is plus when time is outside the entanglement interval. So when time is less than L1 here, the sign is positive, but when the time is within the entanglement interval between L1 and L2, the sign of the I epsilon term is negative. So what happens is, in the limit epsilon goes to 0, Z can take, Z goes to two branches. One, it goes to 1 for time outside the entanglement interval, and it goes to e to the power 2 pi I for time within the entanglement interval. For Z bar, there is no such problem. For all times, the sign of the epsilon remains the same, and hence there is only one limit in the epsilon goes to 0 limit, that is 1 for Z bar. Now, what do these limits of the cross ratio mean in terms of the locations of the operator on the uniformized plane? In epsilon goes to 0 limit, W1 by W4, it goes to 1 for time outside the entanglement interval, and it goes to e to the power 2 pi I by n for time within the entanglement interval. Whereas the ratio of the anti-holomorphic locations of the operators in on the uniformized plane, they always go to 1 for all time. I'll show what this means diagrammatically. So when Z goes to 1, what it means is that these locations of the operators on the same slice are coming close together. So two operators on the same slice are coming close together, whereas the other branch where Z goes to e to the power 2 pi I, the operators on adjacent slices, they come close together. This is crucial in obtaining the results that we get. So for times outside the entanglement interval, the operators on the uniformized plane on the same slice come close together, and for time within the entanglement interval, the operators on adjacent slices on the uniformized plane come close together. Here so our aim is to get a universal correction to entanglement entropy at order epsilon square, a universal time-dependent correction. So here it is shown that to evaluate second Renyi entropy, we need to get this log of this 4-point function on this on like a n-sheeted surface. So for the second Renyi entropy, it's only 2 sheets, so it's a 4-point function. This 4-point function, this Renyi entropy at leading order is known. So it is given by the step function, where here the magnitude of the entropy inside the entanglement interval is related to the quantum dimension of the operator. Plus, there is a correction at order epsilon square. And what we find is that this correction at order epsilon square is given by this time-dependent function, which is universal. And I will show how we obtain this using conformal block argument. So using conformal blocks, no, this is, yeah, it's general. Yes. Yeah, yeah. So the second Renyi entropy is given in terms of this 4-point function GO, where GO is essentially it's this diagrammatically. This is what it means. GO is the magnitude of this this scattering taking place using any operator OB and sum over all operators OB. And this is written as a decomposition in terms of conformal blocks, FO. U bar are new cross ratios which are defined in terms of Z and Z bar. Now, for our calculation, we only require the vacuum conformal block. And for vacuum conformal block, B is 0, H, that is the conformal dimension of the exchange operator, is 0, and the coefficient is 1, and this is the vacuum conformal block. Using this vacuum conformal block in these expressions, this value of the second Renyi entropy is obtained. In the limit, for regions outside the entanglement interval, that is in the limit Z bar going to 1 and U bar going to 0. And substituting these values of U and U bar in epsilon goes to 0 limit, we obtain the correction at order epsilon square, which I showed in the previous slide. Now we want to obtain this correction for times within the entanglement interval, that is for the limit where Z goes to e to the power 2 pi I. In this limit, U bar, it goes to 1 and 0. To get, so here we had an expansion of the vacuum block in powers for around U equals 0. Now what we require is expansion of the vacuum block around U goes to 1. To get that, the following fusion transformation rule for the conformal blocks is used. And this rule for vacuum, it takes this simple form. So here, the vacuum conformal block in the limit U goes to 0 is related to the vacuum conformal block in the limit U goes to 1 via the quantum dimension of the operator O. There are more terms, but these are subleading in powers of U minus 1. Hence, in this region, the change in entanglement entropy is obtained by substituting this expression in here, and we get the same correction to the second Renyi entropy at order epsilon square, which I showed earlier. So this is the answer for the second Renyi entropy at order epsilon square. This was the argument for second Renyi entropy, and this can be shown for a general nth Renyi entropy as well, that is the time dependence. Yeah, so it looks like this. Okay, I have some plots later on, I'll show. To evaluate the nth Renyi entropy, I had said in the beginning that what is required is evaluation of a 2 endpoint function on an n-sheeted Riemann surface. So what we do to evaluate this 2 endpoint function is take the OPE between two operators on the same sheet. So the OPE of two operators on the same sheet is taken, and this is the OPE. At order epsilon square, this term has contribution from the stress tensor. And when OPEs for each pair of operators on each of these sheets is taken together, the two endpoint function takes this form where it is given, the epsilon square term is given by the sum over the stress tensor at each of these sheets. So what this simplifies to is that the correction to Renyi entropy at order epsilon square is just given by the expectation value of the stress tensor on this n-sheeted surface. Since it is given by the expectation value of the stress tensor, that is why the result that is obtained is universal. So this is how the second Renyi entropy, the nth Renyi entropy looks like. So it is given by the expectation value of the stress tensor. And this expectation value of the stress tensor on such a surface is non-zero. It is because if we use the transformation of the stress tensor to the uniformized plane, the expectation value of the stress tensor on the plane is zero, but there is a non-trivial contribution because of the Schwarzschild of the transformation. And it is this Schwarzschild which contributes to give the correction to nth Renyi entropy at order epsilon square. And yes. Yeah, so for h not equal to h bar, there will be h and h bar here instead of the delta O coming out common. I think it will be, this is h plus h bar, so yeah, that will be h and h bar in the coefficients. Yes, so this term will dominate. So it's h here and h bar here. If h is much larger, this term will dominate. Yeah, I can show it. Yeah, so this is one of the examples, and the red curve is the plot of SL, of the correction at order epsilon square, the sum of SL1, SL2. That, yes, the step function. Yeah, so these are the plots for minimal model theory. I'll come to this. So for this theory, this exact result for epsilon is known. So that's why we have this plot for second Renyi entropy. Yes. Yes. Now we want to obtain this epsilon square correction in the large interval, large time limit. By large interval, I mean that, so on this, here, L2 is taken to infinity first, and then we want to look at large time. So what this means on this n-sheeted surface is that we have taken L2 to infinity. So here L2 is taken to infinity, and we want to probe at large time. So t is large, and at large time, instead of seeing the system with, so this, what happens is it doesn't see the beginning of the entanglement interval. Or at large time, what this geometry essentially becomes is a cylinder with period n beta. These surfaces were periodic with period beta. And now for large time and large interval length, the geometry effectively becomes one cylinder with period n beta. So the expectation value of the stress tensor on this n-sheeted geometry in this limit, it just becomes the expectation value of the stress tensor on a cylinder with period n beta. And now using the thermal expectation value of the stress tensor and substituting it in this formula here, we obtain the correction to nth Renyi entropy at order epsilon square, and this is the answer. And this matches with the L2 going to infinity and T going to infinity limit of this answer. I will give an example of the minimal model. We'll consider a p prime minimal model, CFT, with p greater than p prime, and central charge is given by this formula. So for minimal models, the 4-point function is known in terms of hypergeometric function. So we can evaluate the second Renyi entropy exactly. We can get an exact result in terms of epsilon, no epsilon going to 0 limit. So here I have given the entropy for an operator phi to 1 of conformal dimension this. And here, just to check that we reproduce the epsilon square term that we got through universal arguments, we have expanded this exact result of second Renyi entropy in powers of epsilon. And we find that indeed this term is the same as the universal correction obtained earlier using general arguments. So here is a plot. As shown earlier, the step function at epsilon equals 0. This is the plot of second Renyi entropy with time. The blue curve gives the full answer of the second Renyi entropy with time at some finite value of epsilon. And the red curve is the result, this result with the leading value of the second Renyi entropy plus the order epsilon square correction. And we find that for times very close to the ends of the entanglement interval, this correction it's a good approximation to the exact result. So here, as you can see, it's very close. And this is the zoomed up version. And for times quite close to the end of the entanglement interval, the epsilon square result remains valid. So I should make a remark that the epsilon square result that we have, it's valid. It's valid everywhere except very close to the ends of the entanglement interval, because that is where the perturbation in small epsilon, it breaks down. Yes. Here is one example of values for which the step function is very small. So the quantum dimension is very small, so there is no correction to, there is no change in second Renyi entropy at 0 order in epsilon. But for this minimal model, this is the exact result in epsilon, the blue curve. And the red is the order 0 plus order epsilon square term plotted. And we see that it's actually the order epsilon square term which is capturing the full exact result in this case, because the conformal dimension is very small and the contribution to the second Renyi entropy at order 0 and epsilon is 0. Next, I will, so we find agreement of this result at order epsilon square with holographic entanglement entropy. So a CFT perturbed by a heavy operator of conformal dimension delta is dual to ADS with a massive point particle which starts its motion at a distance epsilon from the boundary, and it falls towards the black hole horizon as time progresses. And the mass of this particle is proportional to the conformal dimension of the operator in the CFT. Presence of this massive particle leads to a back-reacted geometry in the bulk, and this geometry is given in this paper by Takenagi et al. And so in this back-reacted geometry, the entanglement entropy can be computed using the geodesic length, and the geodesic length of a geodesic with endpoints at L1 and L2 on the boundary. So it's a dual with points L1 and L2 on the boundary, and a geodesic length is calculated. And so entanglement entropy is related in this manner with the geodesic length. So in this paper, this calculation is done. We expanded the result in powers of epsilon and extracted the order epsilon squared term, and we found matching of the universal time-dependent correction at order epsilon square with the result obtained from CFT. It's a conical defect geometry. Next, we have also looked at the correction to the nth Renyi entropy at order mu square epsilon square. So for this, we considered a CFT with non-zero spin 3 chemical potential, and it is disturbed by a local quantum quench of finite width. We show that the leading mu-dependent correction to the Renyi entropy of the excited state occurs at order mu square epsilon square, and the step function at order epsilon 0 is unaffected by the correction at order mu square. The time dependence of the correction at this order, epsilon square mu square, is universal, and it is determined by the 3-point function of the stress tensor with the higher spin currents on this n-sheeted surface here. So this is, I've just given the result of the correction at order epsilon square mu square, and this correction is given by the 3-point function of the stress tensor with the higher spin currents W, evaluated on an n-sheeted surface. And we have obtained the result for the full analytic form of the time-dependent correction at this order. We have obtained the exact result, and it is given in our paper. It's very long to quote it here, but I just quote its limit, this limit where L1 is put to 0 and L2 goes to infinity. And the claim is that this correction is also universal because it is given by a correlator of the currents. Here is a plot for the correction at this order. So these are the plots for. So I will give a limit of time going to infinity, and there it becomes a finite result. This is the plot for the correction at order mu square epsilon square with respect to time. This is the plot for the entanglement interval from 0 to 1. Those are the ends of the entanglement interval. And these plots from bottom to top are for increasing values of beta. We were able to do all the integrals here and obtain the result at this order. So to check that full result, we consider this large interval, large time limit. And in this limit, again, the 3-point function on n-sheeted Riemann surface, it reduces to a 3-point function on a cylinder of period n beta. So this limit is where the interval is taken to be infinity first, and then time is also taken to be large. Hence, it becomes a simple problem of evaluating the TWW correlator on a cylinder of period n beta. This correlator is obtained by using word identity on the WW correlator. This is known, and then word identity is used on this correlator, and we obtain this result for the order epsilon square mu square correction for large interval, large time. And this result, it matches with the large time limit of this whole function, and in fact, with the large time limit of the full result that we have. The TWW correlator is evaluated on a cylinder with period n beta. So that is where the n comes. Yes. Yes. So this is the correction to nth Renyi entropy. Also, in this regime of large interval, large time, we obtain a result at order mu square epsilon square for a higher spin current of general spin S. This is obtained by acting with the word identity on this correlator of where these W currents are now general higher spin currents with spin S. And the following correction is obtained. So I'll just summarize. We study the time evolution of Renyi and entanglement entropy following local quantum quench in a 2D CFT at finite temperature and finite width. The time dependence of Renyi and entanglement entropies at order epsilon square is universal, and it is determined by the expectation value of the stress tensor on an n-sheeted cylinder. We have checked the epsilon square result matches with the holographic entanglement entropy for time less than L1. And we have also considered a CFT deformed by chemical potential mu of the spin 3 current. And we find that the time-dependent correction at order epsilon square mu square is universal. We have found this correction and we have shown that it is universal. In future, what we are working on is trying to get the order mu square epsilon square result from holography. This requires a formulation of a dual to the quench in Chern-Simons theory with higher spin fields. That's it. Thank
you. Is there any idea what the higher dimensional analogs of this computation would be? Like,
yeah, we are thinking of that too.
Again at order epsilon square, I think, with just the stress tensor exchange. But is the corresponding geometry known, the holographic geometry?